Assalamu alaikum students. Hope you are good. Today we will start with the chapter number 7, flash separator. Okay, um, flash separator play a very important role in petroleum and petrochemical industry. Okay, whenever you want to separate the phases, you want to separate the more volatile components from the less volatile components. Then in that situation, you need a flash separator. Uh, the difference between the flash separator and distillation column is because in distillation columns we have different types of trays. However, in flash separator we don't have any of the trays. However, we have what you called demister, which is attached to the flash separator. So in flash separator, if you can draw a flash separator, I will show you how it looks like. Flash separator can be a vertical and can be horizontal. Okay, for example, in this case we have a flash separator where your feed is entering and you'll get some product which is highly volatile on the top of the flash separator, and you will get some uh, less volatile components at the bottom of the flash separator. In flash separator we always have a demister. Okay, the purpose of demister is like during this separation of volatile components with non-volatile components, because the volatile components are moving up, they may take some of the non-volatile components along with them, and those non-volatile components have a little bit bigger molecular size as compared to uh, the volatile components. So we have volatile component. If for example volatile component, I think there's a problem with the spelling. So volatile component that has a molecular size that much, for example, okay, and you have a non-volatile component, volatile component, the molecular size is that much big. Okay, so during this separation, when this non-volatile component is moving up, when this is moving up, they are taking some of the non-volatile components along with them, and when they wanted to pass through this demister. The demisters, they have a mesh screen which does not let the non-volatile components to move up. Okay, and they will only allow the volatile components to go up. So in this way, we are making sure that here we are having only volatile components, and here we have non-volatile components. Okay, so this is how you do flash separation. If you look at this flash column, it has an empty space. Okay, we don't have any trays here. Okay, but in distillation column, which is a little bit uh, taller than flash column, and they have the trays also. So that is the difference between a flash column and distillation columns. There are some flash columns which are horizontal in nature. Okay, they are horizontal. If somebody is asking, okay, then where we use a horizontal flash separator? If you have a horizontal flash separator, normally we use in a situation where we want the gravity to separate the components. If you have, let's say, if you have liquid 1, if you have liquid, two different liquids, and similarly you also have gases. So in that situation, what you do, you pass this component here and let them to stay inside the flash separator. After some time, what happen, the liquid which are highly denser in nature, they will settle down on the bottom. Okay, let's say in this case is liquid 1. Similarly, the liquid which are less denser will stay on the top or separated on the top of this layer, the first layer, and whatever is left here is gases on the top. So this one is liquid 2. So now you have two different liquids separated from each other because of their density difference, and the gases which are lighter in nature will stay on the top. You can remove the gases from the top. Okay, you can remove this one from the bottom of the flash separator, and you can even have some portion, some exit here for removing this part of the liquid here. Okay, so this kind of a column is basically also known as, this kind of a separator is also known as gravity separator. Okay, so because we are using gravity to separate them, that's why it's called gravity separator. Okay, so far I think you are able to understand what is horizontal flash separator and what is vertical flash separator, and where we use vertical flash separators are only used when we have the components which are volatile and also less non-volatile, or you can say heavy components. Only that situation we use vertical flash separator. Good thing about this one, they cover less surface area, cover less what you call area, not surface area but area inside the inside your industry. Whereas this one, because it is horizontal in nature, they will have large area, they need a large area inside the industry. Okay, but obviously the purpose of this one is totally different than this one. Hope you understand the concept of flash separators, even though you already studied before. I'm not sure that you studied before, but if you studied before, then you will have an idea that where we use the separators, the horizontal separator and the vertical separator. Coming back to the chapter flash separator. So this chapter begins with the problem to find the flow rate of a liquid and the vapor outlet streams. So what we are going to find out is the flow rate of the liquid stream which is coming out at the bottom of the flash separator, and the vapor outlet stream which is coming from the top of the flash separator. Okay, in steady state mode, obviously we are working in steady state mode in Aspen HYSYS, but you can use dynamic simulation. But the one of the criteria for dynamic simulation is that you must complete the steady state mode before you can switch to a dynamic mode. So in steady state mode, the separator divides the vessel content into its constituents. Okay, as I told you before, you have the feed that is entering. That feed is divided or separated inside the vessel. Vessel is separator. Uh, they are separated into vapors, which are volatile components, and liquids, which are less volatile component. The vapor and liquid in the vessel are allowed to reach to equilibrium. So you are only able to separate the components when you reach when you separate the liquid, you will reach to a stage when you have equilibrium. Mean no more liquid will be separated at the bottom and no more vapor will be separated at the top. And before the separation has been done, you will allow them to reach to vapor and to reach to equilibrium before you can have the separation. If you remember the equation that we have, we always use this simple equation for separation. K is equal to y over x, where this one is vapors and this one is liquid. So this is the distribution coefficient, how this will be distributed and how this will be distributed between vapors and liquid. Okay, how your feed will be distributed between. So this is basically also known as equilibrium constant. Equilibrium constant. Okay. So the only way we can do the separation when we reach to the equilibrium. Okay. Let's go back. So flash separator is performed to determine the product conditions and phases. Okay, whatever the condition of the product is, product in this case is vapors, which is coming from the top, and a liquid, which is coming from the bottom, and what phase they are. Either they are in liquid phase or they are in vapor phase. Even vapor also, on the which when we get on the top, we can condense them into a liquid form also. Okay, depends on the customer. The pressure at which the flash is performed is the lowest feed minus the pressure drop across the vessel. So the pressure which we are working with, or the pressure at which we are performing the flash, is basically is the lowest feed pressure. Okay, make sure lowest feed pressure minus the pressure drop across the column. Whatever the pressure drop that you have across this column, that one, this feed minus the pressure drop, that is the pressure that this flash is occurring. Okay, so the enthalpy is combined feed enthalpy plus the or minus the duty. So this is the enthalpy we'll have in this case. The separator has the ability to back calculate results in addition to the standard application completely defined feed stream being separated at the vessel pressure and enthalpy. The separator can also use a known product composition to determine the composition of the other product. Okay, so a separator can work like this. If you need to provide the feed composition, and then it will separate the components into feed and into products, which is vapors or liquid, or if you can provide the composition of the ending product of your product, and based on your product that you are getting, it will back calculate the results and find out what is the composition of the other products, and if even for the beast feed also for the balance. Okay, so either you can provide the feed composition or feed information, and they will calculate the product information for you, or you can provide the product information and they will back calculate the feed information for you. Okay, so in this chapter we operate a flash separator in HYSYS to model the flash separation process. So the idea of flash separation process, we already have in our previous concepts. What we are doing is we are using the same concept inside Aspen HYSYS. Okay, like always, we start with HYSYS. We select the components, we define and select food package, and then we will specify the material streams, and then separator. Okay, so I will move this this window to one side. I will make two windows, and then I will start the process of flash column. So like always, the first thing you need to do is you need to select the components. So I will go into the components, and if you look at the problem statement, first let me read the problem statement, and then we will go to the Aspen HYSYS. So we have a stream containing 15% ethane, 20% propane, 60% of isobutane, 5% of normal butane at 15 Fahrenheit and atmospheric pressure. So we have 1, 2, 3, 4 components at a temperature of 50 Fahrenheit and atmospheric pressure, and we have the flow rate of the feed. Remember the units, these units are in pound mole per hour, and here the temperature is Fahrenheit. This stream is to be compressed, okay, before we let this feed enter to a separator. We are compressing it. I will tell you later on why we are compressing the feed, and cooled to 32 Fahrenheit. Okay, the resulting vapor and liquids are separated as two product streams, which are flow rate and composition of two streams. Before I jump into Aspen HYSYS, I wanted to add a little bit more concept regarding why we are compressing and cooling it down, this feed. Okay, I will show you in terms of HYSYS also how we are able to understand this concept. But to understand the concept, we need to see the phase diagram. So if you go, let me go down. Okay, so if you do if you remember the thermodynamics class, what we are doing basically is like, for example, if you have the x and y axis, and here you have the pressure, and here you have the temperature, and if you draw a phase diagram of multi-component, it should look like this. The pressure temperature diagram, you can call this one pressure temperature diagram, or even phase envelope. Okay, you can call this one either of the names. Okay, so you know that on this side we have liquid, and this side we have vapor, and this side we have liquid plus vapor. Okay, to do a separation between vapors and liquid, it must be you must be working, your pressure temperature condition must be in a way that you are in this particular region. Okay, because in this region only we have the separation of vapors, liquid and vapors. In case if your pressure temperature condition at which you are working in industry is this one, you will not expect to get a liquid in the product, or both. You will only able to get the vapors if your conditions, or if your pressure temperature conditions are in a way that you are here. If your pressure temperature condition, if your temperature is very low and pressure is very high, you are in this region. If you are at this region, then obviously you will only get liquid. If you do separation, you will not get vapors, you will only able to get liquid. In order to get liquid and vapor, you must be in a region where inside the phase envelope. Only in this region, if you're working, you are able to get liquid plus vapor in your products. Okay, so the idea is you must be fall inside the phase envelope in order to get the liquid and vapor. Now the question is, if your conditions are here, how you are able to fall inside? Obviously there are many ways to go inside. As I told you, if you're working at a higher temperature, this is a very high temperature, right? You're working at a very high temperature, so very high temperature and a high pressure also. So if I somehow manage to make this part enter into the phase envelope, then I will be able to do the separation properly. So first thing we can do, in order to make sure that it is in the middle of the phase envelope, to get a perfect separation, should be in a region where you have maximum amount of liquid and maximum amount of vapors. So I can do one thing, I can just cool it down. So if you cool this stream, what you are doing, you are moving this part to enter here. You're moving this part to go inside, right? The second thing we can do is to even pressurize. How you can pressurize the vapor stream? By using a compressor. Okay, if you are using a compressor, what you're doing, you're increasing the pressure. So you increase the pressure from here to here. So now your position will be inside this region. So when you are inside this region, now you have a very good separation. Now vapors plus liquid plus vapors. Okay, so all you are doing is cooling down, cooling it, okay, cooling your stream, cooling your feed, and all you're doing is compressing it so that you are inside the phase envelope. So when you are inside the phase envelope, you can get a perfect separation of vapor and liquid. This is the same concept that we are using in the question. Okay, the same concept is used in this question. you are going to compress it. Obviously in this case we are compressing it first and then we are cooling it down. The idea is same. Okay, you want to enter into a phase envelope so that you will get perfect separation and to avoid the one phase region. That's the main reason why we are doing all this procedure. So the resulting vapor and liquids are to be separated into a product stream. I will tell you in inside. I think I told you before, but even here also we will go again, and we will see how we can draw a phase envelope, and we'll see like where we are at that particular moment and when we are separating. Okay, so the resulting vapor and liquids are to be separated as two product streams. What are the flow rates and the composition of two streams? Now here they're asking you two things. One is the flow rates and they're asking you compositions. Okay, make sure it's rates, flow rates S, and compositions. Sorry. So you need to calculate the flow rates and the composition of two streams. What do you mean by two streams? The product streams. How many product streams you have in flash column? Two product stream. One is on the top, which is for vapors, and one is on the bottom, which is for liquid. Okay, so let's start by adding components first. Our components are ethane, propane, isobutane, and normal butane. So I will select the first one, ethane, and select the last one, which is normal butane, and then add the component in just one click. Once you add the component, the second thing you need to do is select the fluid package. So the fluid package we have in this case is Ping-Robinson equation of state. Okay, so we select Ping-Robinson equation of state, and then we go to simulation environment. As always, we need to create first material stream. So we drag one material stream and put it in the center. Okay, and we can just open that one. Before I open that one, I want to make sure that my units are correct. So the temperature units I have is Fahrenheit and the pressure unit I have is atmospheric. So I will go back to the unit set. I will go to pressure and change the pressure. This we are already doing before in the previous simulations. So I'm going to find out the pressure is. So pressure here is an atmospheric. Change into atmospheric pressure, and the temperature we have in Fahrenheit, and also we have the flow rate, which is mass flow rate, or molar flow rate is in terms of, here it is molar. So we will go to the molar flow rate. It should be in M molar flow rate, and change that one into pound mole per hour. Okay, there are 2 pound mole per hours, both of them I think is the same. Okay, and then you can press OK. Now again we go inside to the stream, and the first thing I will change is the name of the stream, which is in gas. Okay, obviously we have ethane, propane, isobutane, and normal butane. All of them are gases, so it should be gas. The pressure, the temperature we have is 50 Fahrenheit. The pressure we have is 1 atmospheric, and the mass flow rate in pound mole per hour, it will be 100. If it is given to you, fine. If it is not given, please assume 100. Okay, then the fourth thing we need to provide is the composition. We go to the composition and we can provide here. This is in percentage, so I will convert that into mole fraction. 0.15, 0.2, 0.6, and 0.05. It should be overall total one. Okay, then press OK. It is completely defined. So the material stream is completely defined. Now, as I told you before, according to the question, the stream has to be compressed and then cooled. So for compression, we need to use a compressor. Okay, so we add a compressor. If you look at here, the pressure is mentioned in terms of pound per square inch. Don't worry if it is mentioned. You know how to convert the unit inside the simulation also. So what we need to do is now we open up the compressor. I can call this compressor a simple compressor. Okay, and we already have the inlet feed stream, which is the gas stream. We should provide the energy stream, so I will put Q, or you can even call this one comp.q. Okay, so in order to make sure that this energy is for the compressor stream, this energy stream is for compressor, we put comp.q. We don't have the outlet, I can call this one comp gas, means compressed gas. Okay, now since compressor require one information at the end, which is if you go to the worksheet, go to the pressure, and here we provide the outlet pressure of the compressor, which is 50 pound per square inch absolute. So I will put 50 and then I will change the unit from here. So once you provide that information, the compressor will also fully define. So once you define the compressor also, you will see a simulation looks like this. So if you look at here and look at the previous simulation, now we start building up. Okay, now we are making the streams, and then we are attach the streams together, even the different unit operation we are attaching now. The next thing we need to do is, according to the statement, we need to cool down this feed after compression to 32 Fahrenheit. So for that we need to use a cooler. Okay, we are not using heat exchanger, but we are using cooler. Cooler is a simple device, so just click, and heater is the opposite to cooler, which is shown here. Okay, if you want to heat something, you need to use heater, and if you want to cool something, you need to use a cooler. Okay, so again, open that one. I can call this one, you can leave it like this also, but I can call this one cooler. The inlet to the cooler is compressed gas, which we already created before. The energy stream to make sure that it is not similar to the previous one, it should have a different name. Okay, so remember, don't use the same name for different streams. If you use that one, they will coincide in the simulation. So what you are doing instead is you are making a different energy stream name, cool -q, and for the outlet we can call this one cool gas, since we are cooling the gas and this cooler is using to cool it, so we can provide. Okay, now obviously the cooler has some pressure drop, but in this particular case we are assuming that there is a zero pressure drop. And in order for the cooler to work, we need to provide at least one information for the outlet of the cooler, which is, in this case, is the temperature. And then the temperature that we have for the outlet of the compressor is 32 Fahrenheit. So we are cooling it from 135.7 to 32 Fahrenheit. Once you provide that information, in that case the cooler is also fully defined, so you will see a simulation like this. So we are building one by one. Okay, you can even go inside, and if you go to design and parameter, you can even check, find out the duty which is calculated here. It might be a little bit different than this one, because this is an old version and this one is a new version, so maybe you have some difference in the calculation, because every new version they are adding more and more information. That's why your results are more accurate in the new versions as compared to the previous one. Now this is your feed that is inside the phase envelope, and now you have it's the right time to use a separator. So if you look at on your screen, you have a separator which look like this. Okay, so you select that separator and you put it in the center. Okay, so it is a vertical separator. As I told you before, vertical separator is used for system which have gases which are more volatile and non-volatile components. Okay, double click and open this one. I call this one with the name separator. Okay, and we already have the cool inlet stream, which is cool gas stream, which we have already from here. Okay, we don't have the top stream. I can call this one top, and for the bottom I can call this one bottom. Okay, so if you look at here, the only thing we provide is the top and bottom and we connect this with the feed, we don't need anything else in this situation to find out the answer. This energy stream is optional. Optional means if you want the product at that certain temperature, if you're thinking that your separator is not working, your separator is the separator conditions are different than the feed conditions, then you can provide different temperature and pressure here, different temperature conditions here. In that case you need energy stream. Okay, but if you are using the feed information, whatever the condition that the feed this feed has, and using the same information inside the separator, then you don't need to provide the energy stream. Okay, remember this one. If you are using the feed conditions to run the separator, you don't need to provide energy stream. If you want to change the conditions, and if you want that your product coming from the top has different conditions than your bottom, then you need to use energy streams. Okay, so depending on what you want to do. So far we already define everything, and separator is fully defined now. What is asked us to do is to find out the composition and the flow rate on the top and bottom stream. So how to find out the composition? We first click on the top and we click on right and we show table. So if you go to the table, here what we need flow rate. We already have flow rate, however we don't have a composition. To find out the composition, you double click and open. You remove the temperature and pressure because it is not required, and you want to add variables. What we want to add? We want to add composition. So what you are writing here, or what you are going to find here for the composition, is called master component. Okay, so if you click master, if you search master, you will get many different master component. You have the composition in terms of mass flow rate, you have the composition in terms of mass fraction, you have the composition in terms of molar flow rate and also mole fraction. You even have the composition in terms of volume flow rate and volume fraction. However, we require molar flow rate, mole fraction instead of molar flow rate. So I click on the molar flow rate. Maybe if you have a Aspen HYSYS 8.8 or 8.6, then you cannot have the ability to select all of them together. But in latest versions, you have the ability to select all of them together. For example, in this case, I select ethane, I press shift and I select the last one, and then I click on this arrow. It automatically adds all the composition in the table. So if you look at here, we have the composition for the top stream added on the table. Similarly, you can do it for the from the bottom component. You click on add and open. You don't need temperature and pressure, so just remove that. You need composition. So again, you need to find out master. Okay, when you click on master, you will see many different information. So what we need is master mole fraction. So click on master mole fraction, select the first one, press shift key, click the last one, and then add the component, then click done. Once you've done that, you can see all the composition and the molar flow rate is added. All the composition and molar flow rate is added. If you compare the molar flow rate at the bottom with the top, you can see here we get 76% molar flow rate on the 76% separation, and we get mostly liquid, and we have only 23% separating on the top. Okay, so majority of the feed is separated in the but goes to the bottom. Only a small amount will go to the top. Okay, so this is how we do separation. Okay, and together we have separation. Together we have overall simulation looks like this, and your flow sheet looks like this. Okay, so we completed that one. So here what you need to find out is the molar flow rate, which we already find out here. We put it here, and we have the composition. Similarly for bottom, we have molar flow rate and composition. Again, for every simulation you do, please make sure you need to save it. So click on file, save, and save it anywhere you want to like in the computer, so that later on you can use that simulation. Okay, so we have some study here. I will leave it to you to do this one. Okay, if the cool gas temperature is 10 Fahrenheit, so if you look at here, this gas, cool gas, previously we put cool gas temperature 32 Fahrenheit, right? So if you change this one to 10 Fahrenheit, then what will be the changes here? Okay, so for this purpose you need to write it down, this composition first on the paper, then change this temperature in the cooler, and then see what is the changes happening here, and then write down the change information on the paper, and then compare. Okay, what is the what you have if the temperature was 32 Fahrenheit, and what was the composition flow rate if the temperature is 10 Fahrenheit. Okay, so I hope you understand this whole process of separation. For today's lecture I might not be able to come online, but I will ask you to do the practice the whole in 1 hour. Just you can practice this one also, and you can practice the what you call the previous lecture also. Okay, do the practice both of them, and then send me your video along with the simulation in my email address. Make sure you need to make the video also. Whenever you are performing some simulation, please make a video and then send me the video file in my email address in order to check, okay, that you are doing correctly. And make sure when you do the simulation, you first save your simulation before you start the simulation. Save it with your ID. Okay, once you save with your ID will appear on the top, okay, here. So it will make sure that you're not copying the simulation from anyone, you're not copying the video from anyone else. Okay, so it is your own video. Fine, so do like this. Okay. Okay, thank you very much for listening to me. If you have any questions regarding this, please don't hesitate to ask. Take care and bye.